So today we are going to talk about diffraction and refraction, which two terms that you can easily get confused, but by the end of today you'll be experts. So we're going to talk about interference and diffraction in two and essentially three dimensions, starting with 2D superposition, Huygens principle, and two-slit diffraction. Talk about diffraction gratings and the uses of diffraction in biological sciences, in fact. Then we'll switch to refraction and talk about what happens to waves which go from one medium to another medium. It's the phenomenon of refraction. Talk about Snell's law and end on total internal reflection with some fun demonstrations here. So now, last week, where did I leave you? We had this laser set up. So I turn off the room lights. You remember that we have the laser passing through these two slits, and on the wall, on the far distant wall, what we see is the central maximum for where the laser went straight through the two slits, and then on either side there are dots, and a whole series of dots which get fainter and fainter as you get away from the central dot. Now, that phenomenon is due to the diffraction of light passing through the two slits. And what do we mean by that? Remember that when we had a single source emanating, it's spreading its waves out in all directions, and then we had a second source. We showed this last week, that when they interfere with each other, you can have directions in space along which they interfere constructively, and then directions along which they interfere destructively. So what our job is now is to try to figure out for every point in this two-dimensional space whether you get constructive or destructive interference of the waves emanating from these two sources down at the bottom. And what you can see pretty clearly from this animation and from the demonstration we just did here is that there are certain directions in space along which you do get maxima, and they're indicated here by the red arrows. And then in between those are directions in space along which the waves tend to cancel all the time. You get no wave coming out. And in the case of the laser beam there, that's the gaps in between the dots that you see on the wall. So our job now is to try to calculate these directions. How do we do that? Well, in order to do that, we're going to start with a very old principle called Huygens principle, first postulated by Christian Huygens, who lived in the mid-17th century, back when they had either really cool hair or great wigs. I'm not sure if that's a wig or his real hair. And the ruffled collars, maybe that'll come back in fashion someday, though I hope not. He came up, after studying wave phenomena, came up with the hypothesis that every point in a wave medium can be thought of as a point source of circular, or in three dimensions, spherical waves emanating from that point. So if you have waves traveling in water, every point in the water can be thought of as emanating out circular waves. That seems a little bit odd because we see waves marching along as plane waves, even in water, right? Waves hitting the shore of the ocean are coming in like big lines. They're not all spreading out. Well, here we have a single point source of waves emanating out. What happens if we add the wave from its neighbor? Well, here all I've done is drawn the same circular pattern of waves, but displaced by a little bit coming from the next dot over. Well, what happens if we do this for a whole line of point sources and add them all up? Well, you can sort of magically see what happens. You get this line, this line. These wave crests are suddenly now forming sort of coherent plane waves, right? You have a wave crest here, a trough, a crest, a trough, and these would be moving outward in that direction. So yeah, a whole set of point sources of waves can give you plane waves traveling in a certain direction, like so. So if we can take that principle and apply it to this situation of diffraction and try to figure out the directions of the maxima, as you'll see. It works really well. So now, that's how we're going to imagine a set of plane waves is really coming from a whole series of point sources of circular waves. That's kind of cool. It's pretty amazing that he thought of that long ago. How he came up with that, that's, and why did no one think of it before that? That's always the case in science, isn't it? Okay, so now when we have our laser beam hitting a slit, you can think of that as a plane, a set of plane waves, wave crests hitting this slit, and the slit then acts like a point source for light coming out. And then from this point, light is emanating in all directions, maybe not uniformly, and if you actually do the mathematics for a finite width slit, you'll find that the intensity has to fall off at high angles. That's why we don't see a whole row of dots across the wall up there, is because the slit has some finite size. It's not a point source. It's very narrow, but it's not a point. So now all we need to do the two-slit problem then is to add a second point source, and then we'll just figure out in space where these guys add up and where they don't. Well, it looks a little bit complicated here, but there's a better diagram that we can draw to represent this. And that looks like this. Oh, wait, we'll get to first. What we're going to want to do is calculate the directions in space. But to do that, we need to first think about what does this depend on? What will these directions depend on? Will they depend on the frequency, the wavelength, etc.? So let's do a clicker question. Oh, looks like I'm counting up. That's okay. We'll go to about 2 minutes. And I'd like you to talk to each other and ask yourself whether it depends on the source separation, the wave velocity, the wavelength, etc., or frequency, and choose one of these combinations of things that we need to take into account in order to calculate the directions of the maxima. So go ahead and discuss with each other. This is